All right. In this one, we are going to talk about implicit differentiation. Implicit differentiation. Now, it's kind of a scary name, implicit differentiation. But unfortunately, that's what. Um, I mean, it's a process, so it has to be given a name. But really, if you go by like just by definitions, um, then maybe it's more obvious because what we are saying is this is what we are saying. We are saying that dx over dx is 1, right? What does that mean? This means the rate of change of x with respect to x is 1, which makes sense, right? Because what you're saying is you make this table and you put x and x. Now these entries are going to be the same. So however the top part changes, that's how the bottom part changes. So this is always going to be 1. But dy over dx is not necessarily 1. Because because y is not x. We don't know anything about y. Similarly, dz over dx or d elephant over dx, all of these things are unknown unless additional information is given to us. Okay, because derivative basically measures how one thing changes with respect to the other, right? So d square over d circle, it basically measures how square changes as circle changes. That's all. Okay, so that's what you need to keep in mind when doing implicit differentiation. So for example, if I have x squared plus y squared equals 10, and then I say I take derivative, yeah, with respect to time, let's say, or let's do first with respect to x. So I want to see how the things on the left side of this equation and the things on the right side of the equation change with x. So basically, in terms symbolically, that means I'm doing d over dx of x squared, d over dx of y squared, and d over dx of 10. Now this left part is simple, right? 10 doesn't care about x. Whatever you do to x, 10 is going to remain 10. So what's the change in 10? Nothing. So it's 0. How does x squared change with x? Well, we have a rule to find how that works, and it is 2x, but then it is dx over dx, which is 1. And this is 2y, and then it's dy over dx, which we don't know. We don't know what that is. But we know for sure it's not necessarily 1, unless there is some additional information which tells us that y is x. So this essentially becomes 2x plus 2y times dy over dx equals 0. And now it turns out that now we can find dy over dx. Because if you move things around, now you get dy over dx is negative x over y. So it's a consequence of this means that we can use this to find the unknown dy over dx. That's when it starts getting this name of being implicit differentiation, because there are functions which are implicit in x and y, meaning they are in such a way that you cannot separate the x and the y. You cannot write it as y equals something, right? So in that case, it turns out that when you take the derivative, you can't find dy over dx. So it just becomes a method. But otherwise, if you look at it, it's basically you're just taking derivatives of things, right? So now the same equation if I had x squared plus y squared 10, but now I take derivative with respect to t, some other variable, right? So now I'm doing d over dt of x squared plus d over dt of y squared equals d over dt of 10. Now I'm assuming that I don't have any other information other than maybe I'm guaranteed that, yeah, you know what, x does change with respect when you change this variable t, and y does change when, because otherwise it would just be 0 equals 0. So it does change, which means this would be 2x, but now this would be tx over dt, which is not 1, and this would be 2y, and dy over dt, which is also not 1, whereas this is still 0. So here we can't find dy over dx, right? Here what we can find is, we find that x dx over dt plus y dy over dt equals 0. We find that it satisfies some relation. And typically, if you can, like, if you can actually find something like equals, this is what it is, that's good. If you can't, then even finding some relation it satisfies is also helpful, right? Because it turns out that we're not always able to find something explicitly. So in that case, whatever other information we can gather about it, that's pretty good too. Okay, so let's see. Okay, let's do this one, which was on one of the worksheet. It's gonna get messy. It says find y double prime if x to the 4 plus y to the 4 equals 16. Okay, so once again in this situation, you can go ahead and solve for y in here and find the derivative, but let's try to do it without doing that, right? Notation wise, y double prime means the second derivative. So first derivative, take derivative with respect to x. If you have a notation like y prime, y double prime, it's customary to assume that the derivative is being taken with respect to x. Otherwise, it will be mentioned to you explicitly. D over dx y4, d over dx 16. This is 0, this is 4x cubed, this is 4y cubed, dy over dx, which I'm going to write as y prime. So what is y prime? Is negative 4x cubed over 4y cubed, or in other words, y prime is negative x cubed over y cubed. Now I'm taking the second derivative again, and because, as I've said before, I don't like the quotient rule, I'm going to write this as a product. I'm going to write this as a product, and in fact I'm also going to do an additional thing. I'm going to say this is a constant times that, so I can leave this outside. I can deal with the negative in the end. So then I get y double prime is negative 1. I apply product rule to this. So x cubed negative 3 y to the negative 4. But we're taking derivative with respect to x. So I'm going to get another dy over dx, which is y prime. Plus 3x squared. No prime business there because, there is, but x prime is just 1. So it doesn't really affect. So that's what I get, which is all well and good. I can now distribute the negative. So this is 3x cubed y negative 4y prime minus 3x squared y negative 3. The only thing left to do here is I don't want, if I leave my y double prime in terms of y prime, then it's kind of cheating because I have not solved it completely, right? And because I had to find y prime to get y double prime, so it makes sense that I use that value over here. Okay, so that becomes negative again. Negative 3, the powers of x add up, and the powers of y add up. So y double prime is whatever this nasty equation is. Negative 3x to the 6, y to the negative 7 minus 3x squared y to the negative 3. There were more questions on this worksheet. One of them, the weird shape section, had this sine one. I don't remember what that exactly looks like. The one above that kind of looks like this car on a hill or something. But this one says find dy over dx if you have sine xy equals sine x plus sine y. Right, so again we have a situation where x and y are interleaved, they're meshed together, and they cannot be separated in this case. Right, so in this case it's necessary to realize that it cannot be separated. So I take the derivative, I get cosine xy, and then I take derivative of xy, that's going to be x prime y plus xy prime cosine x, x prime, cosine y, y prime, cosine xy, y plus xy prime, cosine x plus cosine y, y prime. Okay, so if I FOIL this out, this is y cosine xy plus x cosine xy, y prime, cosine x plus y prime, cosine y. Get all the y prime things here, x cosine xy minus cosine y, y prime, cosine x minus y cosine xy, y prime is then cosine x minus y cosine xy over x cosine xy minus cosine y. Okay, so it is complicated because the function itself is complicated. However, the nice thing is that even for a function where separating it out as y equals something, is pretty much impossible, we can still find the derivative. Now, this idea is most commonly used in related rate problems. Right, so in the related rate problems, for example, there was one about resistances in parallel, right? So essentially, when you take an electrical component and you are trying to connect them, right? So you take any component, for current to flow through this, there has to be a potential difference. Think of potential difference as a height difference, right? So for anything to drop with gravity, there has to be a difference of height. Similarly, for current to flow, there has to be a difference in potential or height in some sense, which means that everything has a positive and a negative part. Think of it as higher elevation and lower elevation. And then I have this other object which also has a higher and lower elevation. Now if I want to connect them, there are two ways to do that. Right, so how is that? I can connect the negative to the positive of the other one, or I can connect the negative to the negative of the other one. That's just a natural consequence of math, I guess. I mean, there's no other choices. So because there are these two choices are given special names, right? So let's see, I have plus minus and then a plus minus, and I have a plus minus and I have a plus minus. So one way to connect them is I take this negative, right, and I connect it with the positive. And the other one is I take the negative, connect with the negative, take the positive, connect with the positive, right? So let's say, and then this is connected to this, although that would be a short circuit, but that's fine. And we need a, there is some source of battery or something. So if you look at this configuration, this is, if you move it, they are like lined one after the other. So this kind of connection is called a series, and this pictorially, just by the connection, it looks like they're parallel to each other, so they're called parallel. Okay, so that's why any given component has two possible arrangements. A series and parallel component is a consequence of the fact that there's two ways of connecting the wires, negative to negative or negative to positive, right? Which, that's kind of like the instructions you see when you're connecting your, trying to jump your car, right? They always say, make sure you put the negative of this to the positive. And that's because series and parallel combinations, they have their own uses, right? One keeps current constant, other keeps voltage constant. And if you're charging, you want the voltage constant and all of that. So anyways, that's just so that these terms sort of make sense, and that, they just follow naturally because of the choices you have, just two choices. Okay, so there was a problem which said that when you put these components in parallel, because of the way the current distributes, because of the way the voltage behaves, what you get is that the resultant resistance becomes what is called the harmonic mean. That's the sum of the inverses of the numbers. Then the problem was basically saying that, suppose these are variable resistances. Okay, now that's another thing. It's denoted by this arrow. So these are things like, these are, let's say, they don't have fixed resistances. What you do is you take a big bunch of coils, right, and then you have a switch. So the switch is here, then you're using this much coil, so you have less resistance. You want more resistance, you move this coil to the right, then you end up using more, so you have more resistance, and so on. So essentially you can change it, right? So the problem said that, what does it say? Oh, it says R1 increasing at 0.3 ohms per second. Never mind that, that's just a unit. And R2 increasing at 0.2 ohms per second. And it says, what about R? Right, so to find rate of change, we take derivatives with respect to time. And that's again where implicit differentiation comes into play, because then what we're saying is I'm doing d over dt of r to the negative 1, I'm doing d over dt of r1 to the negative 1, d over dt of r2 to the negative 1. Now typically all of these would be 0 unless information is given to me, but in the problem information is given to me that these are resistances and they are changing with time. So if they are changing, that means their derivative is not 0. So this would be negative r to the negative 2, but I don't know how the resistance is changing with time, right? This would be negative r1 to the negative 2 dr1 over dt. Negative r2, negative 2 dr2 over dt. So what I'm trying to find is this, right? Find. So in order to find that, I want to isolate it. So I'm going to divide everything by that. When I divide, I get dr over dt. Negatives cancel. So this is actually just the ratio of r1 to r squared. And then how dr1 changes, plus the ratio of r2 to r squared, and how dr2 changes. And so it says, what about r when? So there's always a when condition in these kind of problems, right? When R1 is 80 ohms and R2 is 100 ohms. Okay, so let's see, what do we know? We find this is what we're trying to do. We know we know R1, yeah, it's 80. We know R2, we know R. Oh wait, we don't know R. We know dr1 over dt, dr. So we need to find R. But we know R is just 1 over R1 plus 1 over R2, which is 1 over 80 plus 1 over 100. Take the LCM of that. Is that going to be 400? Right, because 80 times 5 is 400, 100 times 4 is 400. So you get 5 plus 4, and you get R is 400 over 9. So now you have everything. And then you just plug in. So here again, we use implicit differentiation, where we are saying that if dr over dt is the rate of change of R, then you give me any function in R and I know how to find the rate of change, right? Because I just follow my derivative rule, and in the end I just plug in R prime, or derivative of R with respect to whatever variable. Okay, this video went on longer than 102. It's wow, 21. It's a pretty long video. However, hopefully it helps. Yeah, the name is kind of scary, but all you're doing is taking derivative. So essentially this is what we're saying, is that if we know, say, dr over dt, we can find d over dt of some function of R, right? Because we know that then this is just going to be f prime R times dr over dt. And how we find the derivative of the function f, well, that's just the rules of derivative. It doesn't care about variables. So like if it's R squared, it's 2R. If it's R to the 10,000, it's 10,000 R to the 9,999 and so on. Right. So this is the essential use of implicit differentiation. It's just normal differentiation. You're just differentiating a different variable, a variable other than itself, right? So you're not taking the derivative of a function in x with respect to x. You're just taking a derivative of a function in another variable with respect to x. So it's just, to me, I think of it as just regular differentiation. Okay, and the video here before I keep talking for longer. And then the last one will be on optimization. I'll go back to look at what kind of problems we've done so far. All right, that's it for this one.